Okay, welcome back, everybody, to the Software and Computing Roundtable after a short summer hiatus. We have a bunch of interesting topics surrounding streaming readout, but before I get to that, I'd like to hand the microphone over to Graeme for a minute. Let me share a screen for an announcement. There you go. You should be able to see it now. Graeme?
I'm just, oh yes, that's come up perfectly. Thanks a lot, Kolja. Yes, it was just to make an announcement that probably some people have heard the fact that we've had an R&D program running here in the EP department at CERN since the beginning of last year. And that also includes a software work package. And as we're now reaching one of these stages where we do a kind of overview of the entire project, it came up that there is a very good opportunity to have discussions between the CERN EP communities and EIC colleagues. So that is going to be, oh, I realize I haven't put the date down, what an idiot. Okay, it's going to be on the 12th of November. That's Friday afternoon if you're in at CERN time. Be more of the morning if you're in the US, and that will include a 30-minute discussion on software, which is at 5 o'clock if you're at CERN time. So at the moment this is being organized by Marcus, Tori, myself and Andre. So we're planning to do a sort of a very quick overview of software activities in EIC, our software activities in the R&D, and then hopefully identify some topics for follow-up after that. So everybody is very welcome to join that discussion on the 12th of November. So yeah, I think that's it. Thanks, Kolja.
All right, you should be seeing the agenda now. And we have a variety of views and experts, and we'll start out, and always first alphabetically will be Roel Aaij from LHCb. I actually saw a press announcement just today that the RK star measurement now has tension close to 2 sigma with the standard model. So that's making inroads, but of course we want a lot more. And to do that, there will have to be an absolute fire hose of data directed at the recording equipment. And Roel will tell us about the software Alan that can handle all of this data and process it online and trigger on it and identify objects. Second speaker is Marco Battaglieri, group leader in Hall B at JLab and co-lead of the ERD23 consortium for streaming readout at the EIC, and he will give us his vision and work on streaming readout and next generation experiments. And we close out with Jin Huang, who's been leading the streaming readout project of sPHENIX's TPC, and also does a lot of work at the EIC. And in fact, I'm pretty convinced there are at least 2 or 3 clones of his, because he always has so many balls in the air and manages to juggle them completely. So first up, I'd like to hand the microphone and the screen to Roel. Roel, whenever you're ready, take it away.
Let me share my screen. Let me see. That's this one. You should be able to see my slides now. Okay, very good. So let me get started straight away. So since I must admit I didn't really know who would be in the audience today, I'll start with a bit of a general summary to the project, and to do that I wanted to include a little bit of some physics. So if I would have to describe the upgrade of the LHCb experiment in a single slide, this would be the plot I would show, where this is the rates of production of various heavy flavor and also charm mesons in the quarks in the LHCb acceptance. And if you look at the the lower PT regions, this goes up to say a megahertz of charm and about 200 kilohertz of beauty produced, and strange quarks are even at the rate of 10 megahertz. So this is an enormous rate of potentially interesting signal decays. And we don't have money. In the end, it's about money to store all this data. The collaboration can only store about 10 gigabytes a second long term, while the full rate of data coming out of the detector at 30 megahertz is about 4 terabytes a second. So that's a lot of data that needs to be reduced. So how do we do that? So there are several stages to this process, where we have 30 megahertz non-empty PP crossings, and the entire data is read out. Then there is the first phase of data filtering, which is called HLT1 for high-level trigger 1, which reduces the data to between 700 and 200 gigabytes a second. This depends on what the data will actually look like, and various optimizations that have to be done once the size of this buffer, which is in the order of multiple tens of petabytes, will be fully known. From there, there is a real-time alignment and calibration running, and once that is completed for a given period of data taking, the full detector reconstruction and selections run as a CPU application. This is called HLT2, and after HLT2, there will be 10 gigabytes per second of data left over. And within this data, about 70% will not store the full raw data, and instead only signal candidates, for example, or signal candidates plus a certain amount of other information, for example, related to isolation, primary vertices, particles that may have been detected in a cone around your signal particles, or as some part of the raw data, some raw banks, for example, for some of the subdetectors. Then there is a bit less than 30% will be full raw data, and the rest is calibration data. And then all of that goes to offline processing. I noticed there's 5 terabytes and 4 terabytes here and there. That depends a little bit on what we will actually get from the detector and the final filling schemes and all of that stuff. Apologies for the confusion. So the challenge of this first filtering stage is to reduce all this data, this 4 or 5 terabytes a second, to about let's say 100 gigabytes a second in real time, and keep all the physics efficiency, of course. So to be able to move all this data, there is a big data acquisition system. You see an overview here with the various LHCb subdetectors at the top, and there are optical links to what is known as the event builder farm. This farm does both the readout and the event building and the first stage of the data filtering as a GPU application. And then these servers are connected by an InfiniBand network to do the event building, to do all the reshuffling of the slices of data that come in from all the various parts of the subdetectors. And then from there, it goes to this buffer storage over regular Ethernet. And then it goes to the second step. And of course, there is fast control as well. And all of this happens in a data center that is on the surface of the LHCb experiment in these sort of container data centers. There are 6 containers installed all in all. So originally, a CPU application was built to run the first stage of data filtering, so HFT1, but a relatively small team of people proposed instead to do this on GPUs and developed the application, which is called Allen, after Francis Allen of IBM, that does this completely on GPUs. One of the big advantages is then that because the data reduction happens inside the event builder farm, the network, the second stage, which originally was 100 gigabits Ethernet, would now be reduced to 10 gigabits, which is a lot cheaper and quite a lot simpler. And in practice, what we did is we replaced the fast Ethernet network cards with GPUs, and then use the onboard cards instead. So that resulted in a nice cost saving. We wrote TDR last year, and you can find it at the link. And this was last year selected as the GPU application was selected as the baseline application. So we are now in the process of commissioning it, actually. So what does the Allen application consist of? So it is a standalone software project. We've tried to keep the dependencies as small as possible. You do need a C++17 compiler. We use Boost, ZeroMQ, and the MS guideline software library, core guidelines, so also known as CPP GSL. We have built-in physics validation, a configurable sequence of reconstruction and selection algorithms, custom memory manager that manages both host and device memory. It runs on CPUs, on NVIDIA GPUs, and on AMD GPUs. All the GPU kernels are written in CUDA, but we have a small compatibility layer that makes everything work with the AMD runtime with the HEP / ROCm environment as well. It's about 100K lines of code now, and if I would have to take a rough guess, about 90% of the code was written effectively from scratch. Of course, we have integrated it with the wider stack of LHCb software and the LHCb data acquisition and control system. So in the end, we started in February of 2018 with a few people. And after only 15 months of development time, the project was reviewed as a viable solution for run 3, and then later accepted as the baseline in May 2020. So this was quite a development feat, to be honest. So what do we do inside the application? So the LHCb detector, in case you've not seen it before, this is a side view, is a forward arm spectrometer, where the interaction point is all the way on the left of the image of the overview inside the vertex detector. There are a number of sub-detectors, rich detectors for particle identification, tracking detectors, the UT and sci-fi detectors, calorimeters, and muon stations. And in practice, the HT1 reconstruction, so Allen processes everything except data from the rich detectors and the hadronic calorimeter. The electromagnetic calorimeter was recently added, which is why it's not on this slide yet. This is still a bit a work in progress, but showing a lot of promise. And we do a lot of things you may know: raw data decoding, track reconstruction, some Kalman filter, secondary vertex finding, primary vertex finding, and then a number of selections based on single tracks, 2 tracks, muons, and other sort of inclusive physics signatures. Just to flash a few reconstruction performance plots, we get to above 90, I think even 95% track reconstruction efficiency over nearly all of the PT range, with ghost rates in the order of 5%, which is very good. And then for the vertices, we also get above 95% reconstruction efficiency, and the muon ID efficiency is above 90% with a fake rate. The plot is not here, but which is below, depends on the range, somewhere between 5 and 10%. Off the top of my head, all the plots are in this figure document linked on the right of the slide. Then for the general purpose selections, which we test on a number of signal decay simulated samples, we have an integrated efficiency of 50 to 80%, which is really front to back, and from, say, decay products in acceptance to event selected. This is, of course, we are still trying to optimize this a bit further, but all in all, it's pretty good. And we aim for an inclusive rate of selected events of about 1 megahertz, which corresponds to the roughly 100 gigabytes a second that I mentioned before. This also implies that the event size is about 100 kilobytes per event. So when we wrote the TDR, we measured the event throughput on a number of GPUs. And this was where we were at the time. So the best performance we had was an NVIDIA professional line GPU. We can actually use this because all of the application is written and all of the algorithms only use single precision. So there is no requirement for double precision, which opened the door to use also professional type cards, which are much faster at, or at least are good at single precision, much slower at double precision, but we don't care about that, and significantly cheaper than the data center variants. At the start, we were also looking at consumer cards, but in the end, we decided against using those, although you can see the performance is pretty good. And of course, they are another significant step cheaper than the professional cards. Then in a few months, we went from, say, 85, 90 kilohertz on this Quadro card to more than 150. So this is a more recent picture of the throughput. I should also point out that if you would plot a line where the theoretical number of flops would be plotted against you would do a fit to these data points, you would get quite a nice linear scaling of theoretical flops to throughput, which shows us that if we want to go further or buy newer hardware, then that any gains in the hardware should translate directly to performance in our application. And unfortunately, the most recent performance plots have not been approved yet, so I can't show you those, but we do, of course, have performed measurements also in the latest generation of cards, and we again observed this scaling. So that has helped us actually a lot. So in addition to the general sort of general overview of the application of the project that I wanted to give, I also want to focus the rest of this talk on more the integration aspects. So integration with, for example, the data acquisition system, data input, which has to happen in the data format that is produced by our event builders, data output, which is then transposed to event by event for selected events. We do that because a large-scale transposition of data has to be avoided to make sure the memory traffic in the servers is at an acceptable level, and that means that that means we don't do the transpose, and the events come in batches of about 30,000 events, which we call multi-event packets, and these are grouped. So 30,000 events by each front end. So you get 30,000 events from the first front end, then from the next front end, and the next front end. And a detector may have up to, say, 50 front ends. So this is not your standard, I have all my data of one event close together in memory layout. And we had to take special care in the application to make sure that that wouldn't cost us any throughput. And then we have found sort of the working point that works best in most cases to process batches of events, about 1,000 events per sort of stream, or what is in a CPU we call this a thread, but on the GPU it's called a stream. And then we have order 10 streams, so we have about 10,000 events in flight on each GPU at any given moment in time. And then we have to make sure we do this correctly. Of course, the whole thing has to be steered by the experiment control system. We have to do error handling. We have to do failover in case one of the GPUs decides to give up. This should cost us as little data acquisition time as possible. We need access to detector information, geometry, alignment, for example, and we do this by obtaining this information from the rest of the LHCb software stack on the fly. So we have components of the LHCb stack running at the same time, which we communicate with to get this information. We have to deal with changing conditions. So at some point, if the alignment calibration decides to update things, this has to be propagated. Of course, we have to provide monitoring for data quality and shifters. And the HT1 processes and the hardware share the server with the event building. So we must make sure we don't step on each other's toes in terms of CPU and memory. And that is one of the things that we've been testing recently. So on the right here, you see a photo of one of the event builder servers. This is a gigabyte server with 8 PCI Express slots, dual socket server, a lot of RAM. I think we went for 500 gigabytes of RAM, which is very nice. And these PCI Express slots in the end contain 3 readout cards, which we call TEL40s, 3 readout cards, 2 InfiniBand network cards, and 1 GPU. So we had to really optimize the layout of the hardware in the server to make sure that the memory traffic between the two NUMA domains, which you see here on the left and the right of the plot, was as small as we could get it, because we were afraid that this interconnect, what is called XGMI here in the schematic, would be a bottleneck. So that's why we chose this data layout. And then we've been testing this with generated data, because while we have some simulated data, the event sizes are a bit too small to do proper testing. So we did a test recently where we ran with 10 event builder servers, and then they generate data scaled to such that everything matches what we will get in the end. Then the HT1 application consumes this data, and we test it with one GPU without reconstruction, still, just to make sure that all the transfers were working as intended. And we also ran the front ends in data generator mode, with the goal to verify that all the I/O and throughput requirements work, and that a single GPU could handle the data load. Because in terms of throughput, we reached the threshold of being able to process everything with a single GPU per event builder server, but we had to verify that also in terms of memory and PCI Express traffic, this works. So on the right, this is a screenshot from the LHCb control system, where you see for this test setup the event builder process, receiver units, builder units, and then the Allen processes running on the GPU. And these square blocks are shared memory buffers, which we use to transfer data between applications. Now, this was very successful. So with this setup, we could reach 43 megahertz of generated event throughput. Of course, we only need 30 in the end, so that gives us a lot of headroom, which was very nice to see. We saw that at this rate, the PCI Express throughput to the GPU was actually the bottleneck. I think we reached about 24 gigabytes a second. That's not the theoretical limit, which should be 32 gigabytes a second, but we think there might be some overhead or some runtime issues. So we are looking into that. At least this is more than enough for what we need. Some important things that we learned is that taking care of technical details such as proper NUMA domain aware running of your applications, both in terms of CPU and especially in terms of memory allocation, reading and writing, and also details internal to the device runtime can be very important for the throughput. Also use an optimized build. That's saved. At some point I was running the debug build and that cut the throughput in about half. And while we had some monitoring, you can see an example on the right here. This is monitoring of the shared memory buffers that we use to verify that all the events, all the multi-event packets, all the data was going through. We definitely need some more. This week is actually a beam test at CERN, and the monitoring is one of the core focuses for the activities, because when we hope to see some beam, I think not this weekend, but the weekend after, and then we better have an idea of what's happening in our application. So to summarize, our GPU application was selected as the baseline solution. We actually purchased the hardware recently. Both NVIDIA and AMD made a bid. In the end, we went for the NVIDIA RTX A5000 card. So the order has gone out. I think they should be delivered by the end of the year. We are still trying to improve performance, both in terms of physics efficiencies and the throughput of the application, but we are mostly focusing on commissioning now, integration, consolidating everything, and as much testing as we can do. And the real data that we should hopefully get from the beam test in a week and a half will help us a lot with that. So careful consideration of data flow, memory, networks, NUMA domains, device runtimes is really crucial to make an application like this work. So we had this larger scale integration test that was a success. Now with the beam test, we'll scale up probably another order of magnitude. So that'll be an important milestone again. And there are very exciting times ahead already now. And next year also, of course, when we get real collisions again. Thank you very much.
Thank you, Roel. Very impressive work, very comprehensive slide.
I think you've muted yourself, so we've lost your audio.
I'm sorry. Very impressive work. Very nice slides. Before we go to questions, I have to announce that Marco had to leave us because he received some very serious news. So we will continue with Jin after this, but we also have more time for discussions. So I think Doug had his hand up first. Doug, go ahead.
I joined late, so if you mentioned it, I missed it, so I apologize. But are you using the GPUs for the actual event building? And if so, why did you make that design choice?
No, we are not doing any event building on the GPU.
Okay, so it's just in the CPUs on the boxes.
Yes, indeed.
Okay, thanks.
Jin.
Thank you. So it's a more operational question. I'm very curious about the frequency needed for alignment update, and it's something when we run at RIC, we need to do at every magnet ramp, and I was just wondering how frequent LHCb need to update that.
So this depends a lot on the subdetector. So one of the key physics signatures in LHCb, because its heavy flavor mesons is displaced tracks, because the mesons fly some distance inside the detector, and the precision with which you can measure, for example, the displacement through, for example, the impact parameter is dominated by the distance of the first hit in the vertex locator to the collision point. And to get that as close as possible, LHCb has a movable detector. So the vertex locator moves about 3 centimeters once stable beams are reached.
Wow.
And is then about 5 millimeters away from the beam. So the closest hit is about 5 millimeters away from the beam. So before the start of the veil, the detector is open. And then once stable beams are declared, by reconstructing vertices with only the left half and only the right half in real time, we know where the beam is, and then the detector moves to its closed position. Of course, then you want to do the alignment for at least for the 2 halves of the vertex detector, basically every fill. So that one is updated every fill. The rest of the tracker alignment is updated every few fills. The muon state alignment is done maybe twice a year, and other calibrations, so the rich calibrations, but this is not for HD1, but more for HD2, are done per run, because the which is sort of 20 minutes to an hour of data taking, because their gas detectors, and both the pressure and the temperature in the cavern affect their resolution. So this is calibrated with the shortest time scales. But for the HD1 applications, this is not an issue. So updates are expected kind of 5 minutes after the start of data taking, because then you get a new vertex locator alignment, and then well, maybe every few hours, typically once every fill. It's about 10 hours.
I see. So you also answered my second question. That is, it's lead to only a 5 minutes latency for Ellen to ramp up to use the new alignment. That's very impressive. Yeah.
So, well, the latency. So these 5 minutes is the alignment task doing its work, because what they need. So what they need, the tracks that they need is regular physics tracks, and they like these tracks that from beam gas interactions that traverse most of the vertex detector. So it takes a little bit of time to collect those, but order maybe 100,000 events is enough, and that's not even a second of data taking. So and in the past, all the tasks were distributed over the farm. So there were say 2,000 tasks all doing a part of the work to reconstruct with and find all the residuals, and there was one master task that was calculating new alignment constants, and then the iteration between these was orchestrated by the control system. So that will probably work in the same way. Because all the applications are multi-threaded now, it may be that we don't need the full farm anymore, but just a single 64-core server, something like that. That this is something that will be commissioned, say, end of this year. People are now working on getting all of this back into running shape.
I see. Makes sense. Cool. Thanks very much.
Thank you. Vardan?
Yes, hi. So in the slide 2, you mentioned the buffer in between. Can you tell a little bit more about the technology of the buffer used there, about the performances, latencies, access reliability? Is it in memory storage or a disk storage?
No, it's a disk storage. I must admit, I'm not really up to date on the latest developments. I know this. I think they're going for an object store on old school spinning platter hard drives. We have to write 100 gigabytes a second, which is a lot. So, and that gives you automatically kind of a number of drives that you need. There will be no RAID mirroring or anything like that. It's just if one disk breaks, we lose a little bit of data, but to be honest, this is so little we don't really care. It's big network attached storage appliances. The last technology I understood was NFS over InfiniBand, but don't take my word on that. I would have to check with my online colleagues what they are planning to do. The way the whole system, the data acquisition system is designed, all of this is decoupled. So if we go to where's my slide with the screenshot here? So all these shared memory buffers, from our point of view, we get multi-event packets, so incoming event data from these two buffers, one in each NUMA domain, and then we write events to the output buffer, and from there it's over to our online colleagues to put it to the storage. In the end, there will be one or two additional applications that read from these buffers and then output to the storage over the network. Okay. And this decoupling makes it much easier to develop things in parallel, or to make changes independently from each other.
It's a very wise decision. My second question is, you mentioned that Alan is using 0MQ. Is it used by main the data transport? Are you using 0MQ over InfiniBand?
No. So the LHCb, the framework used for most of the LHCb software is the Gaudi framework, which is shared with the Atlas experiment. When we started, we didn't really see a way to do batched event processing with Gaudi, because all the existing software was really doing event by event. I think after a few years of development, we should have another critical look at this choice, because the framework Gaudi also provides a large amount of very useful components that we should probably not try to duplicate functionality of. This is a bit of I digress a little bit, but so we have we have our own event loop in batches, and then we have quite a number of threads for input, for steering the various GPU streams asynchronously, and for all the communication between all the threads in the event loop, we use 0MQ, because it makes multi-threaded programming a bit easier. But not for any, the data transfers are just CUDA memcopy async, basically.
Okay. So you're using CUDA API for zero copy?
Yes.
From InfiniBand. Right. Okay, I see.
Yeah. So the event builder, so the shared memory buffers are owned by this EBMBM application that you actually see here, and then the event builder processes write directly into these buffers, and then basically our application receives a descriptor, which is just a collection of is a pointer to a header, and then there is a semi-contiguous sort of 3 gigabytes per 30K events of memory that we can address, and that's what we read directly from, and then we copy directly as big chunks of this memory as we can to the GPU. Here, this was where the run. So there are a few details there. You have to register this memory with the device runtime. That makes a lot of difference in the throughput. And we were copying too small chunks. So that's something we still have to improve, to copy bigger chunks of memory, because we were calling CUDA memcopy too often, actually.
Okay, understood. Thank you.
Graeme, I see your hand is raised.
Yeah, thanks, Roel. It was a really nice talk. My question was about how you introduced the device independence into Alan? Because I think you started the project in an R&D phase with CUDA only, and whether that had much of an impact. And I'll just ask the second part of the question first, so you can give one answer to it. The CPU performance, is that something you need then, for instance, to do trigger simulations on the grid? You might not have a GPU, and is it reproducible as well between running on the CPU and running on any kind of different GPU?
So that's actually 3 questions, but let's see. So
Sorry.
No worries, no worries. They're all very relevant, very important actually. So indeed, we started with CUDA, and then technically what we have is a very thin layer for all the runtime calls, mem copies, and the like. Then for all the kernel calls, effectively what AMD decided to do is replicate the CUDA API, but with their own function names. So we just define one to the other, and then basically it works. You feed it to the AMD compiler with some if-defs in front, and it basically works. For the CPU version, we did something similar, where in a few key places the CUDA calls are like launching a kernel is replaced by a number of for loops effectively, and that does one of the points that you have to do is you have to write your for loops in such a way that if you go one by one, it actually works, and you have to make sure you don't use the thread indexes in a certain way such that everything works on the CPU. The reproducibility we've been keeping a close eye on, so we have builds for both. We run a test that checks that the differences are small enough. In the TDR, we spent quite a lot of time looking at that. We get the per mil level differences, which is sort of similar order of magnitude that you would have if you use various types of instructions, SSE, AVX2, AVX512, whatever you would like to use on the CPU. But this is something that we keep a close eye on for sure. And then for simulation, so the CPU performance is much worse than the CPU HD1 application, but it's peanuts compared to the simulation step. So I think with the single thread, we do a few hundred kilohertz, a few hundred hertz on one core of HD1 CPU, which is more than enough to not be an issue in the simulation. So there we use the CPU only build.
That's great. Thanks a lot.
Douglas? Doug?
My button doesn't.
There you go.
This is a perfect slide to illustrate my question. You have the output buffer, right? I assume it's a memory buffer, correct?
Yes.
What's managing it as the data is going out to your remote storage, which you showed on another slide? Because it's a pipeline, right? So if there's any hiccup and slowdown, somehow that information has to be fed back in, so the Allen processes know to back off.
So the way this is done is we have it's super old school, but so I think the application, the shared memory buffer manager application was developed at CERN, I think for Delphi, or no, for Aleph originally, and some parts of it still survive. I think the developers are actually still the same people. So there is an application that owns the memory, and it also it provides an API where you can ask for an event. You can subscribe to buffers, register yourself. The API is quite straightforward. So you just say on the input side, wait for an event, and then give me you get a descriptor, and on the output side, you say I need so much space to write to, and then you get the space, and then you write your data and you say I'm done. and then you hand it back over to the application. So what we do, there are buffers in between, and the buffers are used to pick up to compensate for spikes. So if there is some batch of events that's a bit slow, or there is a hiccup somewhere, then the in-memory buffers fill up. And in principle, all of the applications are faster in processing the data than they actually need to be. So they're always all the buffers should be empty and waiting. All the applications should be waiting for data. But it can happen that there is a problem somewhere, that for some reason the throughput gets slower. And then what happens is basically there's back pressure. So the various steps slow down until you get to the event builder, which will just discard data to keep everything running. So if there is one machine with back pressure, then you will lose some data according to how much slower you are on that machine. So there are 160 event builder servers. So if one is slower, you would lose, I don't know, 160th of the data. If one event builder server goes down, everything stops. This is a risk in the design of the system, that all the servers have to keep running. If a GPU fails, then there are hot spares, and with the reconfiguration of the data acquisition system, which shouldn't take more than a few minutes, we will be able to continue taking data. And this error handling and failover is something that will spend a lot of time on working well in the commissioning period. That's basically really taking off now. I hope I've answered your question.
Yeah, you did. I mean, basically, if the output clogs, it percolates up, and the event builder then has to stop.
So the event builder, if it's one machine that stops, the event builder will start discarding data to keep everybody else running. If everything has back pressure, then yeah, it just discards.
No, but what I mean is that each machine has internal back pressure.
Yeah,
and so you don't worry if it's slow writing out, that back pressure propagates up to the event builder on the machine.
Yeah, exactly. Yeah.
Thanks.
Jin, I think you have a follow-up.
Yes, a very quick follow-up question to Doc's question. Is the size of the buffer and how long is buffer time? I assume the frequency, the back pressure show up will be related to the buffer time. I assume it's minutes in this case. Is that the correct understanding?
So we have 0.5 terabyte of RAM in the machine. I think we will use 60 gigabyte of input buffer, something like that, maybe 100 gigabytes. I always have to do. I think you get to some minutes of time, but basically it's 4 terabytes divided by 160 per second. It's gigabytes. Now it's actually it's sort of 30 gigabytes a second off the top of my head. So you get you have a few seconds of time, and that's on the input side. So that's not so much, but on the output side you have more time. There you easily get to 2 minutes because the data reduction factor is about 13. But on the input side, it's a few seconds.
Thanks.
All right. We do have time for more questions, but I see no hands raised. So let me thank you again, Roel. Excellent talk. Thanks for the very lively discussion, everybody. And Jin, can you take over?
Thank you very much.
I see there's another hand.
I think that's just Grammy clapping.
Oh, okay. Sorry. Okay, let me share my screen and let me know if it works.
Yep, just appeared.
Okay. Great. Okay, thanks again for the invitation to join this roundtable discussion. And also, so thanks to many colleagues that contributed to these slides. And especially that I would like to highlight a few elements that was discussed in the last streaming workshop and AI for ERC workshop that is at the intersection between computing and stream readout. And so everything that has underlined line here is a hyperlink that we can click on. Okay, so first of all, back to the US side, that as you know, that we have a Red Hammer collider at the RIC, which is a 1.2 kilometer diameter colliding ring, and that currently we are having a stack experiment running with a full upgrade that's showing up this year in the coming run, and then for the next run that we are going to have a major upgrade.
Hold on a second.
Sorry, David. Okay, maybe let me continue first. And also, in the next year, in the next run,
it already sounds bad.
I assume some speaker, assume some audience need to get muted.
I don't believe it for a second.
Hey, David.
Yeah,
David Abbott, mute your mic.
Okay, so and in starting run 23, we are having a major upgrade of sPHENIX experiment, and then that will be a new collider experiment that's added into the grid, and then naturally that in the also middle of this decade, we are also going to upgrade the RIC collider ring into EIC that provide colliding nuclear beam as well as high luminosity polarized electron collisions. And so back to sPHENIX, that we are having a wide range of this program that is supported through a pretty typical central barrel collider detector stack, starting from silicon tracker in the middle, and then large TTC, large XM TTC that is filled the role of a main tracker. So all this tracking detector is a streaming readout, and outside that is a kilometer stack, which is running in trigger mode. And then we have been going through quite a long process of proposing and establishing the project. And right now we are going through the construction and installation phase with the aim to start receiving beam at the end of 2022. So it's very close now. And we are currently right here. And so just to show one slide of progress, this happened about 1 to 2 weeks ago. That's the installation of sPHENIX superconducting magnets at the sPHENIX experimental hall that is inserted onto 13 out of 32 sPHENIX hydronic kilometer sectors that is already sitting on its base. And then on the streaming readout electronics that we having a detector, 3 tracking detectors that is from in electrons is reading out in streaming readout mode, and with a customized electronics that is purposely built for tracking detector for collider mode. And then we having a generic interface card which receiving fiber of custom protocol coming from the electronics, which is interface to a server that is a commodity computing through this large FPGA card. So will be 16-line PCI Express output and 10 GB per second fiber input. And so this is, so it have a link here regarding the reference. And it's also, just one point, it's also serving a very similar role as PCIe 40 using LHCb that we discussed in the last talk. And after that will be a cost network. And besides that, we also having a time interface that try to coordinate every of the readout cards as well as front electronics to run at the same pace as the beam crossing clock. And that is a joint development with Syncron Lighthouse at Brookhaven. And then there's also a few peripheral projects that try to utilize this system like high density ADC and as well as like a fast ADC for time flight detector development. And so quickly show up the data flow that from digitizer to ASIC to Felix interface server and then to storage. just to expand a lot, that just out of ADC, for example, the ADC is built inside many of the ASICs that digitize at every clock cycle, and then we for all the tracking detector we use ASIC for zero suppression. So out of that we had about a bandwidth of 20 terabit per second, just from the front electronics up to the input threshold of Felix readout card in counting house. So we expect to use about 10% of the fiber input capacity of Felix interface. And after that, we have about 5 terabit per second PCI Express bandwidth, and which coming from the Felix interface that already reduced the data through trigger throttling and buffering, and expect to use about 5% of that bandwidth and send that to the main server of Epic, which is also a dual CPU Epic server. And we have 38 of that, which will provide another layer of buffer. This time will be to about 1 minute time scale, as well as running a compression and data sorting on those servers. And that have a network bandwidth of 1.5 terabit per second. And we use 10% that and put onto online buffer in the counting house. And that gives us a time period that we can write through, for example, breakage of external connection of a counting house, as well as importantly to write out the field pattern of collider, so that we only need to transmit out DC data. And now part of the talk is so after that we go out of the just readout domain right to the offline domain. But since it's highly connected, so point out though that in sPHENIX plan to run a fixed latency reconstruction at about 2 weeks of fixed latency, allow us to run all the calibration jobs and having another large buffer disk as a receiving side of the RIC computing center. And some of the audience here also play an important role in this particular task, although not directly discussing this topic. And so currently that we're having developed a plan that try to enhance the use of streaming data, not only taking the streaming data from the tracking detector, but also to write out some of them and to discuss the idea in the next few slides. And it's actually commended by RIC PAC that's encouraging and also praising us that to developing such fixed program based on the string readout, a string readout stream of the data. And currently we have a constructed, we have a complete construction of the just about the Felix card, as well as procured the server, which is currently installed in the counting house, as well as the network structure and also online disk buffer server also starting showing up, so that we are going to take data for in 2023. And so how the streaming data is produced in sPHENIX, if we don't take this, if we don't write out streaming data, is for example taking TPC as example that we have a continuous conveyor belt of time beams that coming from the detector, that every beam is filled with the streaming data, which is a zero suppressed TPC hit. And at a certain moment, we have 15 kilohertz colorimetric triggering, and we only write out, and after every trigger, we only write out about 13 microseconds, which is drift time of the TPC that corresponding to a complete event as a colorimetric trigger. So that is the baseline running of sPHENIX. But we can certainly, since the data, the full minimum bias collision data do arrive at counting house, we could also expand the TPC readout window, for example, to add on more just minimum bias crossings, so that we can record significant more minimum bias collisions. And this actually turned out to be very useful. For example, that if we read out 10% of streaming data that is arriving at the counting house, which is a working point we can tune. For example, if we tune to read out 10% data, that costs about 50% increase of data volume, which we think in PP runs, we can take that. And then that will increase a 500 increase of hard to trigger PP sample. So that's including, for example, 100 kilohertz charm production at low PT, which will be very useful for our heavy available physical program, both for heavy ion physics as well as in cold QCD physics tightly connected to EIC. So diagram about how to do that for both temperature chamber and a silicon strip tracker, as well as ITS2 type of silicon pixel tracker in the bottom. I will now go through the details. And but the impact is quite immediate. That when taking 10% data streaming, we can do previously cannot be done measurement, for example, D0 production at low PT, and then that is going through the untriggered streaming data that we just fish out the D0 signal offline, and this is as one example. And then that can also be done with if we later figure out working point run at 100% streaming readout, that will be another significant improvement of statistical precision. Nonetheless, this could potentially just be one single time measurement that uniquely enabled through the streaming readout data, and also tightly related to EIC, for example, the DD bar simultaneous asymmetry that both try to probe the Gluon-Sievers type of effect. And then, so that also brings us to EIC experiments. And after we upgrade the accelerator to electron ion collision, that there are currently quite a few proposals in discussion and in development for the coming proposal call ending at 1st of December. And just to show a generic EIC detector on the left from the EIC yellow report process. And many of the detector is also considering doing a 100% streaming readout. And so that's part of the discussion here, though. That EIC streaming readout will be quite different from what we do at RIC and at LHC. The basic is that the EIC collision cross-section is very small, 50 microbar, which is 3 of the magnitude smaller than RIC, and also even smaller comparing to LHC, like LHCb observes. And that means even with high luminosity at EIC, the top collision rate at top luminosity is pretty low. It's only half megahertz. And comparing to 10 megahertz at the RIC that sPHENIX is trying to collect, and much lower than what LHCb have to handle as shown in the last talk. And that translated to a relatively low charge particle production rate too. So that means that one of the unique thing of EIC is it's actually a very low signal rate colliders. And while many of the collision signal, even though it could be low PT and quite diverse, they are quite precious. And it's quite tricky to produce a trigger that just be able to guarantee that we just record all the data. However, since also the collision rate is low and with the high luminosity, background control and systematic control is quite crucial. That, for example, we could be vulnerable for synchrone background as an electron machine, as well as the systematic control of many measurements will become the dominant uncertainty for EIC measurements, that we need to be able to do it well. So, putting that into a test, that we just put the EIC event as well as many background events into a simulation, and that lead to, for example, the occupancy of the events that happened on each of the detector. If we can further digitize them with a data format that we currently know, that give out the total collision signal rate of about 100 GB per second. That's assuming about 100% noise, which is a very well controlled noise, by the way. And also, which is a very much handleable signal data rate comparing to, for example, what sPHENIX is built up to do and what LHCb already achieved. So, therefore, instead of picking which collision to save, we can in EIC we can actually choose just to save our collision data in raw data as raw as much possible, so that we can later fish out a signal that we are not considering, for example, today in a high-level triggering. And then it's also important that what we try to throw out, though, in EIC, the important thing is what we try to throw out is not collision or which kind of track. Actually, we're trying to throw out background, for example, synchrone radiation, and also electronic noise, if we happen to be choosing a detector technology that is noisy, which I actually want to encourage the community to try to avoid that. And so that's leads to a quite a different event filtering strategy comparing to, for example, LHCb experiments. and that can do event filtering type of filtering or very highly compressed collision data. And so that leads to a general consideration of EIC detector, EIC real-time system, and just grab a flowchart from the EIC CDR. Probably many of us already seen that in quite a few past talks. That coming from a triggerless readout at the front end. So front end does not receive a trigger signal. It should be able to digitize and zero suppress everything it observes from the detector. And then that is bridged to either front-end processor or directly bridged into a link exchange at a commercial server through a customer link exchange card, which will be able to receive the data further reducing it, and also be able to buffer it to the level of seconds. And at that time, it's the latency, the buffer size is comparable to the Allen system as we just discussed in the last question with Roel. And then that will be able to handle the data just propagating through server and doing further data reduction on the server. So when we put this into the EIC CDR, we try to design the bandwidth of the whole network as tolerable as possible so that we will be able to handle, for example, unexpected noise and the background. And starting with 100 terabit per second, just fiber connection to the readout system, and a fiber connection to the front-end processor, and also 10 terabit per second on the out of 10 terabit per second, that's a fiber readout from the fiber link exchange system to the commercial community. And but still, since our collision signal is pretty low, that I think our goal can be just save out all the collision signal at 0.1 terabit per second, and so that we are not flashing the disk with just noises. And then that leads to that potentially large compression ratios between each stage. And that could be a quite interesting topic for EIC online computing. And just want to also flash that Michael kindly shared his talk with me early on, and sorry to say that he cannot present in this meeting, but it's the boundary between online and offline is quite blurred at the EIC stage, as also shown in the LHCb case, that we would expect many of the processing also get may have offline components in it, as well as we would also try to do a fixed latency reconstruction besides saving a set copy of raw data as contingency, and so that we can start analysis as quick as possible, like the turbo system. And then, so then back to the main readout path. So EIC collision signal is low, but the background is quite uncertain at this moment of design of EIC, and before we can even see the operation of the beam, condition. So therefore, it's potentially that we need to find a way to reduce the noise and background by up to like 3 order of magnitude just on the size of the bandwidth in this particular layout. And we also need to be able to reduce this in a reliable way, in the sense that we try to not lose physics, even if it's not yet clearly laid out today. So therefore, we try to stick with detector features that get filtered out in this step, like cluster and tracks, rather than doing a fixed process selection. And then, so that brings me to 3 topics that just want to I should say just incentivize a discussion rather than go into details. And so the first topic that trying to handle this reduction is especially is like trigger throttling. And that's especially potentially quite important at the beginning of the EIC operation, where background and noise rates could be quite unpredictable and high, and which is experience of many Electron machines. And then that could be quite a very useful contingency method, as we do know that many experiments currently use triggering, and if we have a streaming data that's coming out the front end, doing a throttling can easily reduce the data volume by order of magnitude, so it can be fit into the output bandwidth. And so that could be a well-used hardware trigger, for example, colorimetric trigger to select the EIC electron, that is produce a fixed latency trigger that can be used to throttle even at the front end and the link exchange system, or could be high level trigger if we can tolerate have the data on computer memory, then be able to run, for example, triggering on GPU as in Roel's talk. And then but it do have a risk of physics loss. For example, if we trigger on DIC electron, there'll be many EIC physics that at low Q square may not be able to trigger on that electron. And also we need to handle the systematic uncertainty that's coming from a trigger system, and especially tricky at the beginning of operation. Unless there's also development like Sergey, who is also coming to meeting, working on PID-based trigger on using machine learning with a link to his talk, as well as also a talk in recent AF EIC talk that are doing event topology trigger, which happen also to be trying to fish for highly failure protection signal, as in the LHCb case, but try to do it on IPJ2. So that's another link to that talk. So triggering will be a very effective way to do so, but we need to be cautious about what will be the phase loss that we are going to have if we use triggering. Another method that's also very commonly used is compression. There are like lossless compression algorithm used for decades that can provide a fast compression. For example, a few of them is tested when we just decide to procure the server for sPHENIX. And usually, if we just run the out-of-shell compression, it's really compressed by factor 2, tested on TPC streaming data in this particular case, and at about 10 to 20 GB per second on that server. And there are also ways that we can do, for example, lossy compressions, and that try to adhere to the detector features. And it will be an opportunity to use some of the machine learning tool that especially unsupervised machine learning based on data. One example is this link, which is a talk that from CMS HG Cal ASIC that's doing an auto encoder compression that basically with a signal coming in and you ask a network to shrink it down as much as possible and transmit this particular signal as a reduced data. And later when you use it, you use a decoder to expand it out. And we are also trying to test other neural network architectures that try to do similar thing. One example is so-called Bacillus convolution autoencoder that try to handle a particular problem that autoencoder try to do when we have zero suppressed data that induce a sharp drop in the ADC spectrum. And that we do it by not outputting only one, just a regular ADC data, but also outputting a mask that try to tell which of the ADC bin is likely to contain a signal. And we also comparing that to many of the published lossy suppression algorithm for scientific data that we reach about a factor 30 compression and with a relatively low mean error comparing to many of the algorithms. But we are trying to push to the front of high compression ratio and also a low error in our current test. So that is discussed in one of the talk in our last AF EIC workshop. Okay, and then just just go through the last thing that another well-used data reduction that's just on the detector with the detector focus is feature building. For example, we can do clustering on calorimetry, and Marcus talk actually can talk about the clustering on class 12 streaming data, which will be a very effective way of suppressing single tower analysis. And also tracklet building, for example, the Alice is putting that for TPC data and only record the hit residue, which is quite highly effective in reducing data volume, as well as just the machine learning based of track finding, like we discussed in the last AF EIC workshop. And also, if we have ADC series like a pulse, there's many ways to do amplitude extraction too, which will be another very, I think, effective way to reduce the data on ADC spectrum. On ADC time series that we're going to see on many of the streaming data. Just to highlight that a few of the developments that the community is trying to work on. So a quick summary that sPHENIX is under construction and start taking just about 1 year later from now, which is quite exciting and also thrilling. And so that's currently development on streaming data on top of just a stream readout, just use the streaming data. And I think we can show that just by using the streaming data itself can have a very significant increase of physics capability. And there's a strong link with EIC, both on the technical level as well as on the physics program. And on EIC, and it's a quite unique collider with a very low colliding cross-section comparing to RIC and HC, high luminosity and the strength requirement on systematic control. And I think one of the key developments is with a wide adoption of stream readouts to be able to reliably filtering out noise and background, which currently also is uncertain, but be able to have that prepared so that we are able to take the EIC data in a fully streaming way. Yeah, that's all.
Thank you, Jin.
Questions?
Very comprehensive overview of a whole lot of interesting topics. Jeff, you've had your hand up for a long time now. Go ahead.
Yeah, hi, Jin. I agree. Thank you for that talk. It's very nice. I wanted to ask a question that you did partially actually answer, but I want a more specific question, which is in the sPHENIX, you talked about reduction of the data using the Felix, and you mentioned a whole lot of kind of potential things for reducing that. I'm curious as to what you're actually implementing and what you actually intend to implement and what you actually expect to get in terms of reduction.
Sure. So what we defended in sPHENIX, what we defended in sPHENIX baseline is quite a straightforward reduction. That is simply just a trigger throttling. That when a trigger signal come in, that I recall just allow a streaming data of TPC to go through for a full drift window, and that is a factor 4 reduction. And after that, on the server, there's another factor 2 reduction just by running a very stock compression, lossless compression algorithm. So totally together, these two is factor 10 reduction. That's what we showed in the baseline of sPHENIX project. And what we also want to add is additional recording of pure streaming data that is just beyond the triggered events. And I think that is encouraged by PAC. And that's also quite doable because we're not doing anything fancy. And beyond that, it's just R&Ds. And as you also mentioned, there's quite a few ideas. There's even proposal, I think, get funded. But I think many of them, for example, if you want to do track finding or class finding on Felix, need to be proved to work in a very reliable way to be able to use in a production environment.
Yeah, thank you. Yeah, I was curious how much of that you think can be implemented on the Felix, right? In terms of space on the FPGA and things like this. Of that laundry list, some of those things obviously probably can't be done on the Felix, but some maybe can.
Yeah, I think so. See whether I have a full list somewhere. Probably not in a full list. I think something like a tracking probably will be very difficult. Compression may be possible, but it depends on the patch size that we want to do. But I think many of them do need it's a lot of work before we can show it's actually workable in a production environment. So currently, our program is not assuming that we are running that in baseline sPHENIX, and because we are taking data in 1 year. But I think many of those ideas will be running in a parasitic mode, in the sense that it's getting the data, not actually used to go to the production data, but just running on the side as a proof of concept during the run.
Okay, thank you.
Yeah.
So you're getting kind of a factor of 10 from the trigger windowing and the
and lossless compression. Yeah.
Okay, thank you.
Yeah, that's pretty straightforward. Yeah.
Okay, thank you, Doug.
Yeah, I have 2 questions. One is EIC related and one is sPHENIX.
Sure, please.
Can you go to the sPHENIX slide where you showed the network throughputs and how much you're using?
Yes.
So you didn't have that in the very last. So, you listed as a buffer of a certain size and a few days in the buffer. What's the sort of expected data rate to the outside?
We expect about 100 GB per second. That is after the buffer box smoothing.
Okay, so that
Yeah.
that number.
And
Okay.
yeah, and the caveat on that is will be depends on the collision species, whether it's gold or PP running, and also of course as a new experiment, I'm sure that we'll have surprise the first day we turn on the detector with the real beam, and
Right.
so that's a two caveat. But our current I think party line is 100 GB per second from here to your place.
Because you can,
That is at
because you
STC.
basically said you can dial up how much min bias you want to fill the pipe with.
Correct.
Right.
And also the good news is that's only happened on year 2. So in year 1 is a pure trigger throttling without any beam, without any additional min bias data, for the reason that first year 1 is go-go collision, and go-go collision is so concentrated in collision itself that adding extra drift window does not help in physics program. So therefore, in year 1, it will be just a pure trigger throttling plus the lossless compression, which both of which are well established.
Right. And then my EIC question was more.
This one. Yeah, please.
It's the one where you show essentially the very large output out of the streaming readout. And the question is, how much data are you planning that may actually never? Yeah, this one's a good one. That one's a perfect one to excel either one. But you're writing sort of terabits per second to storage, but how much of that is just, if it's never going to be read, there's got to be some feedback loop if I take data in year 1 and never really read it, to rethink my strategy for year 2, 3, 4.
Sorry, I'm not sure I get the
write once,
question.
read never data.
Sorry?
Has low science, write once and read never data, even raw data, has low scientific value.
Okay, sorry, Doug, let me just try to understand the question.
The question is, you're
yeah.
basically sending out from it can be here, it's on terabits per second. That's a lot of data, right?
Yeah,
but if
it's
this
about the
data
level of
is really,
sPHENIX, yeah.
But if the data is not really read again, then you can write quite a bit to raw storage. But if it's just not read ever again, then we should really think these whole pipelines so that the physics quality data, the data that scientists use for doing physics measurements, calibrations, whatever, is really what we capture for perpetuity.
Yeah, sure.
So maybe I can make a comment on this. I'm sorry, Jen, go ahead.
Yeah. Yeah, David, please. I was showing our slides here.
I was just going to say you're 100% right that if we are writing lots and lots of disks or data to raw storage and we're never reading it again, at some point it becomes a wasted resource. So, but I think we have to design it with this in mind, because we don't necessarily have the confidence until some point after we've taken some of the data to start throwing that away. And then we can have those discussions and decisions later. Because I know this is pretty close to what LHCb did when they first turned on, because even they were a little nervous about throwing it all away. So they stored a bunch of data for some temporary amount of time to give them some confidence they really hadn't thrown away anything useful. But I think that's the stage that we're going to be at. Is we're going to have to design it in to accommodate raw storage, at least in the first year, until we really gain enough confidence to start considering not storing it. Does that answer what you're getting at?
Yeah. I mean, the beginning of any experiment, you do things a little different than you do when you hit steady state.
Right.
If I may, my 2 cents, I think I agree that we need to have some kind of parallel data pipeline for data quality assurance, as far as I understood. The question is some percentage of the data which will be processed real time or near real time and sent back and feedback.
So in sPHENIX, we plan to do a few percent. just for quality insurance purpose. I think in Phoenix, we try to do in real time is also like percent level of computing. And then in few days level, we can construct a big fraction of events just on computing farm, so that make sure, for example, more high level observable is okay, like chip size. And that requires the full event to get reconstructed out. So therefore, I think minimally few percent of events that get reconstructed in a substantial way will be very useful to ensure the data is good to a very high level of analysis. Which is separate thing comparing to the fixed latency reconstruction though, which is really useful for offline analysis. And I think for reconstruction, like few weeks of latency will be sufficient.
Okay, thank you, Jin. I see no more raised hands, but we do have a couple more minutes. So if you do have another question, feel free to speak up. Okay, so let me thank the speakers again and all the audience who participated in the discussion. And I'll see you in about a month with our next roundtable on the topic of detector simulations, both with Jayan and with AI/ML techniques. And I think with that, I wish you a good day and close the session. Thank you.
Bye-bye.
Thank you, Koyam.